In this BocaPhysics video, you'll see a set of simulations demonstrating Amperes Law. Amperes Law states that the line integral of the magnetic field around a closed path is equal to the amount of current that is enclosed by the path times the permeability. This law is useful in solving for the magnetic field only for those systems that exhibit a high degree of symmetry. Let's first consider a long straight wire that carries current I, which is uniformly distributed across the wire. Let's assume that the current is directed in the z direction. The first task in applying Amperes Law is to determine the direction of the magnetic field. By the right-hand rule, if your thumb is in the direction of the current, then your fingers will curl in the direction of the magnetic field. So in this case, because the current flows upwards, then your fingers will curl around in a counterclockwise direction, and the magnetic field will everywhere be in a circumferential direction. Another way to determine the direction of the magnetic field is as follows. There are three directions: the z direction, the radial direction, and the circumferential direction. By the BocaPhysics law, the magnetic field is perpendicular to the current. Since the current flows in the z direction, the magnetic field cannot be directed this way, and we're left with the two possibilities of radial direction and circumferential direction. Consider first the possibility that the magnetic field has a radial component. If we reverse the direction of the current by the BocaPhysics law, the direction of the magnetic field must also reverse. However, reversing the current is the same thing as turning the wire upside down. Since the magnetic field is not going to change from pointing outwards to inwards or vice versa, just because we flip the wire upside down, we deduce that the magnetic field has no radial component. This leaves the circumferential direction. By symmetry, the magnetic field must have the same magnitude at all points equidistant from the wire. In this simulation, we've constructed two Amperian loops, both of which are circles which are coaxial with the wire. Let's first consider the outside loop. B will come outside the line integral, leaving only the length of the path, which in this case is the circumference of the circle. Notice that the current that lies in the plane of the Amperian loop is highlighted. On the left-hand side of Amperes Law, we get 2 pi s times b, where s is the radius of the outside Amperian loop. On the right-hand side, we get mu naught I. Hence, the magnetic field B is equal to mu naught I over 2 pi s and in a circumferential direction. Next, consider the inside loop. The left-hand side of Amperes Law still gives 2 pi s times b. S again represents the radius of the Amperian loop. However, the right-hand side will be different because only that portion of the current that passes through the loop contributes to the magnetic field evaluated along the loop. We can write a volume current density that has value I over pi r squared because the current is uniform. R is the radius of the wire here. The right-hand side of Amperes Law is mu naught times the integral of the volume current density over the area contained within the Amperian loop. The right-hand side of Amperes Law gives mu naught I times quantity s over r squared. Solving for b results in b is equal to mu naught I s over 2 pi r squared in a circumferential direction. Amperes Law can be used to solve for the magnetic field of any long straight wire that carries current as long as the current density depends only on the radial distance. Let's next consider a wire that carries surface currents density K. As in the case where the current was uniformly distributed across the wire, the Amperian loop will be a circle which is coaxial with the wire. Notice that only the current that lies in the plane of the loop is highlighted. The left-hand side of Amperes Law once again gives 2 pi s times b, where s is the radius of the Amperian loop. The right-hand side will be mu naught times the integral of the surface current density along the path. For the loop outside, we'll have mu naught k times 2 pi r. The k equals I over 2 pi r. So on the right-hand side of Amperes Law, we'll once again get mu naught I. Solving for b results in mu naught I over 2 pi s in a circumferential direction. If we consider the inside path, we see that no current passes through the loop, so the right-hand side vanishes. As a consequence, the magnetic field inside the wire must also be zero. Let's Let's next consider a current sheet that carries surface current density K, and let's assume that the current flows out of the screen in the x direction. The first task is to determine the direction of the magnetic field. Since the current is in the x direction and the magnetic field is perpendicular to the current, this leaves the possibilities that the magnetic field has components in the y and z directions. That is to say, the magnetic field could have components pointing to the right, or to the left, or up, or down. So let's first consider the possibility that the magnetic field has a component pointing up or down. If we reverse the current, then the magnetic field will also reverse. This means that if the current flows into the screen, then the magnetic field will flip from pointing upwards to pointing downwards or vice versa. However, whether the magnetic field points towards a plane or points away from it can depend on which way the current flows in the xy plane. Hence, the magnetic field can have no component in the z direction, and we conclude that the magnetic field can only have a component in the y direction. By the right-hand rule, the magnetic field points to the left above the plane and to the right below it. By symmetry, we reason that the magnetic field has the same magnitude at all points equidistant from it. Construct an Amperean loop that is a rectangle which is perpendicular to the current sheet and which lies halfway above and halfway below. Only the current that lies in the plane of the loop is highlighted. Let's assume the loop has length L and width W. The left and right legs contribute nothing to the line integral of the magnetic field around the path, since, as we just concluded, the magnetic field points to the left above the loop and to the right below it. The line integral then gives the sum of two terms, minus b times minus L plus b times L. And this is just 2bl. The amount of current that passes through the loop is K times L. It follows that the magnetic field has a magnitude mu naught K over 2 and is directed to the left above the plane and to the right below it. The remarkable feature is that the magnetic field has the same magnitude regardless of the distance away from the loop. This is analogous to the situation in electrostatics, where the electric field had the same constant value of sigma over 2 epsilon naught at all points above or below a charged sheet. Consider now a current sheet that carries volume current density J and is of thickness 2A. Let's assume that the current flows out of the screen in the x direction. The direction of the magnetic field can be determined the same way as for the current sheet that carries surface current density K. It is found that the magnetic field is directed to the left above the midplane and to the right below it. Furthermore, by symmetry, the magnetic field vanishes on the midplane. Let's construct a rectangular Amperean loop that is perpendicular to the current sheet and the bottom side of which lies in the midplane. Only current that lies in the plane of the loop is highlighted. Further, assume that the length of the loop is L and the width is Z. As before, the left and right sides contribute nothing to the line integral of the magnetic field because the field is perpendicular to those sides. Also, the bottom side contributes nothing because the magnetic field is zero there. Hence, the left-hand side gives only BL. The right-hand side gives mu naught times J, the current density, ZL, where ZL is the area of the loop. We conclude that the magnetic field B has magnitude mu naught JZ above the midplane and is directed to the left. By similar reasoning, it is found that the magnetic field has magnitude mu naught JZ below the midplane and is directed to the right. If the magnetic field above the sheet is desired, then redraw the Amperean loop such that its top side is above the current sheet. Only that current that flows through the loop contributes. Following the same reasoning as in the previous example, the left-hand side of Ampere's law gives BL. This time the right-hand side gives mu naught times JAL, where AL is the area of the current that passes through the loop. We conclude that the magnetic field B has magnitude mu naught JA above the current sheet and is directed to the left. Likewise, it has magnitude mu naught JA below the current sheet but is directed to the right there. The remarkable feature is that the magnetic field is uniform above the current sheet and is uniform below it. In our final simulation, let's consider a long solenoid of radius r, and long meaning that we can ignore end effects. The windings of such a solenoid can be approximated by a stack of circular loops. In this way, the current is assumed to flow only in a circumferential direction, ignoring longitudinal contributions. The windings of such a solenoid could also be replaced by a surface current, with surface current density K is equal to Ni, where N is the number of turns per unit length. The first task is to determine the direction of the magnetic field. Since we assume that the current flows only in the circumferential direction, this leaves the possibilities that the magnetic field has a component in the z direction and has a component in the radial direction because the magnetic field is perpendicular to the direction of current flow. Consider first the radial direction. This means the magnetic field would point towards the solenoid or away from it. By reversing the direction of the current flow, the magnetic field would also reverse its direction. However, reversing the direction of the current flow is the same thing as flipping the solenoid upside down. But whether the magnetic field is pointing towards or away from the solenoid can't depend on the orientation of the solenoid in space. Hence, it follows that the magnetic field has a component only in the z direction. If the current flows in a counterclockwise direction, then the magnetic field will be in a positive z direction. Let's construct two rectangular Amperian loops, both of which lie in the same plane as the axis of the solenoid and two sides of which are parallel to the axis. Assume that the length of the loop is L. Consider the outside loop first. We just reasoned that the magnetic field can have no component in the radial direction, so the top and bottom parts of the loop contribute nothing to the line integral of the magnetic field. Let's assume that the right-hand side of the loop lies very far away from the solenoid. Since the magnetic field must get vanishingly small as the distance from it increases, the contribution from this side must also be zero. This just leaves the left-hand side of the loop, BL. However, because no current passes through the loop, it follows that the magnetic field along the left side of the loop must also vanish. We conclude, therefore, that the magnetic field must vanish everywhere outside of the solenoid. Next, consider the loop which lies partway inside the solenoid and partway out. The top and bottom sides contribute nothing to the line integral of the magnetic field because they are in the radial direction and the magnetic field has only a component in the z direction. The right side contributes nothing because the magnetic field vanishes everywhere outside a long solenoid. This just leaves a contribution from inside, BL. This time the loop does enclose current. Only the current that lies in the same plane as the Amperian loop is highlighted. The amount of current that passes through the loop is KL, and K has value Ni, where N is the number of turns per unit length. We conclude that the magnitude of the magnetic field inside is mu naught Ni in a positive direction, z direction, if the current flows in a counterclockwise direction. The remarkable feature is that the magnetic field vanishes everywhere outside and is uniform inside the solenoid. Notice further that the radius of the solenoid doesn't matter, nor does the length, as long as the end effects can be ignored.